Welcome, kiddos, to our further understanding of acid bases and bases. Today we're going to look at pH and pOH calculations and our understanding of pH and pOH. So you absolutely need your calculator. And with your calculator, I want you to move with me through some examples of how to find pH, pOH, and how to find the concentration of the hydronium ions and the concentration of hydroxide ions. Okay, so let's talk a little bit about pure water. Pure water actually self-ionizes, okay? It's kind of cool. It's called auto-ionization. So it contains hydride ions and hydroxide ions, but their concentrations are so low that a conductivity test is negative. So water, pure water, is not an electrolyte, even though water self or auto-ionizes. In a sample of pure water, about 2 out of every billion, okay, that's pretty low. 2 out of every billion molecular collisions are successful in forming hydronium and hydroxide ions. So even though it does do that, it's so low, 2 out of a billion, that we don't doesn't cause water to be an electrolyte. Water is a molecular substance. It does not conduct electricity. In pure water at SATP, remember SATP, standard ambient temperature and pressure, the hydronium ion concentration is very low. It's about 1 times 10 to the power of -7. That becomes really, really important, kiddos, because this helped us understand the pH meter, okay? This concentration is often negligible and will show no conductivity unless very sensitive equipment is used. Okay, let's talk a little bit about about water and what the heck's going on. Adding acid to water adds extra hydrogen ions or hydride ions, causing the hydride ion concentration to increase. Thus, it makes the solution conductive. Adding base to the water adds hydroxide ion concentration, causing the hydroxide ion concentration to increase, making the solution also conductive. Now, it's not like this disappeared. Even though our understanding that it's the hydronium ion, it's actually used interchangeably with the hydride ion. So if you see that, don't freak out, it's fine. You just have to know that it's interchangeable. Aqueous solutions exhibit a wide range of hydronium ion concentration from more than 10 moles per liter for concentrated hydrochloric acid. That's a super concentrated acid. This would probably melt your hand or your skin, very corrosive, to less than 10 to the power of -15 moles per liter. That's actually very, very weak. Very, very weak concentration of sodium hydroxide. You could drink that, no big deal. The range is called pH, meaning power of hydrogen. So when you're talking about pH, okay, you're actually measuring the hydronium ion concentration. Or you're measuring the hydride ion concentration. They're used interchangeably. So the negative of the base 10 exponent for the hydronium ion concentration. So what that means is, listen, in order to find the hydronium ion concentration of anything, right, you just take your calculator and you say 10 to the power of the negative pH. So if you had something with a pH of 7, for example, you could still find the concentration of a hydronium ion. All you have to do is in your calculator go 10 to the power of -7. And then you're going to get a concentration. That number, that concentration, is the concentration of the hydronium ions in that particular substance. So power of hydrogen, let's talk about that for a little while longer. This range is called pH, meaning power of hydrogen. Remember, the power of hydrogen is measuring the hydrogen ion concentration in a particular solution. The negative, the base 10 exponent for the hydronium ion concentration. We use this as a formula. So to find the hydronium ion concentration or the hydrogen ion concentration, you just take 10 to the power of your pH and you just make sure it's to the negative pH. If you take a look at this pH meter, here's neutral. We know that neutral has a pH of 7. Where did that come from? It came from this hydronium ion concentration. So the amount of hydronium ions in a solution is 1 times 10 to the -7 moles per liter. This little 7, that became our pH scale for neutral, okay? If you take a look at this, this is way lower concentration than the 10 to the -7, right? So because there's so little, so little hydronium ion concentration, there's actually a pH of 15, which means it's a base, kiddos. Even though we're measuring, because it's pH, right? Even though we're measuring the amount of hydronium ions in a particular solution, it's still you're still measuring the hydronium ion concentration, and because it's so low, it's actually a base. What that tells you is that every acid has hydroxide in it, and every base has hydronium ion concentration. Cool, hey? So in this case, if I'm comparing something neutral to something that's basic and something that's acidic, right? If it's neutral, right, the H3O concentration plus the OH concentration is equal. Isn't that awesome? So that means that there's 1 times 10 to the power of negative 7, right, moles per liter of the hydronium ion concentration, and 1 times 10 to the negative 7 moles per liter of the hydroxide ion concentration. They're equal. So if I add these together, I'm going to get water. Coolness, hey? And then you have to balance, of course, balance the equation. So very interesting. So every acid has a little bit of base in it, and every base has a little bit of acid. If something has a very high hydroxide concentration compared to hydronium concentration, it's a base. And if something has a very high hydronium ion concentration compared to the hydroxide base concentration, it's an acid. So this gives us a better understanding of what the heck is going on. And this right here, kiddos, that's a very, very high concentration when you compare it to that. Because this is 1 times 10 to the power of 1, so it's a positive number. That's a pH of -1. Now you can leave the scale. It's not just from 1 to 14. It's actually, it goes under, like lower than 1 and higher than 14. So you can actually have a base that's like a pH of 16, 17, 18, okay? So power of hydrogen again. Here's some examples of real life things that and their pHs. Blood is probably the most neutral substance we can have. pH of 7, the only thing you're going to have there, it's distilled water, pure water. Let's take a look at lye. Lye, look at this, so high. Lye is what's in all soaps, okay? We just add fats to it like coconut oil, olive oil, or some synthetic fats in order to make it more usable. And if you take a look at battery acid, super low. Very, very strong acid. But you can go lower than 1 and you can go higher than 14. So the pH scale is used to communicate a broad range of hydronium ion concentrations. Most common acids and bases have a pH values between 0 and 14. So again, because it's pH, because all these values are pH, you're just looking at the concentration of the hydronium ion, okay? You can actually measure something called the pOH, and you can guess that the pOH is looking at simply measuring the hydroxide ion concentration. You haven't seen that before, but it's a thing. So changes in pH can be deceptive. Adding vinegar to pure water might change the pH from 7 to 4. While this change of 3 pH units may not appear significant, the change in hydronium ion concentration is actually 1,000 times larger. Every time you move 1 pH, it's actually 10 times, okay? So if I go 2, that's 100 times. And if I move something 3 times, that's 1,000 times stronger or weaker, depending on which direction you're going. So let's take a look at pH calculations. Do you think solutions always have a pH that is an integer, a simple number of like 7, 8? No, okay? They are different. There's a lot of decimal places. Scientists often use pH measurements to 1 or more decimal places. So for our definition of the hydronium ion concentration, we talked about that it's 10 to the power of the negative pH. Must be improved so that we can convert numbers like this concentration, kiddos, to a pH. This is not a perfect number. It's 6.7 times 10 to the power of negative 8. If that's the concentration of the ion, what is its pH? Okay, for that, we have a new formula. There's only 2 formulas, and we use the same formula for measuring hydroxide and hydronium. Okay, pH is equal to the negative log of your hydronium ion concentration. So if you go negative log, and then you put this number there, you get the pH. So pH is equal to the negative log, right? And once you press negative log, you get a bracket right away. 6.7 times 10 to the power of negative 8. The units are dropped because the log has no units, right? and we actually get a pH of negative 7.17, negative 7.17, which is going to actually be 7.17. So that's your pH for this concentration of hydronium ions. You use your negative log, and you simply just put in your concentration of the hydronium ions. Now, I'm not going to test you on this, but let's just talk about significant digits for pH. The number of digits following the decimal point in the pH value is equal to the number of significant digits in the hydronium ion concentration. So basically here, kiddos, you see how 6.7 times 10 to the negative 8 has 2 significant digits? Okay, the first part of your pH is not considered a significant digit, so you have to look after the decimal. That's all I'm saying. I'm not testing you on it. It's just a thing that you should know. It's an FYI. This is definitely 7. It's not it's 7. And then the numbers after that, those are where you have to match your significant digits. But like I said, I'm not testing you on that, and I'm certainly not looking for that on answer to a test. This is just a little FYI. So going from hydronium ion concentration to pH, we use pH is equal to the negative log of the hydronium concentration. And here's an example again of the 4.5 times 10 to the negative 10. If we're looking, if that's our concentration of the hydronium ion, we just go negative log 4.5 times 10 to the negative 10, and we get an answer of 9.35, 2 significant digits. These two have to only match the thing after, the number after the decimal. But to go from pH to hydronium ion concentration, we just go to find the hydronium ion concentration. Simple. It's just 10 to the power of your negative pH. So here's my pH. Let's go back to the hydronium ion concentration. We just go 10 to the power of negative, and you have to always have negative, kiddos. Whether it's negative or positive doesn't matter. Negative 9.35, and you get 4.5 times 10 to the negative 10 moles per liter. So those are your, that's it. That's all you have to know. It's just your negative log or your 10 to the power of. Okay? So since pH has no units, the definition of pH includes the requirement that concentration be in moles per liter. You will need to add the units to your answer. You don't need for pH, but this is always moles per liter. And for pH, right, for pH, there's just pH. So just so you know, we typically use the exponent key, the EE, the capital E, and we try not to use 10 to the power key. This key, if you're using this in your calculator, sometimes it gives you the wrong answers. Usually to get to that EE, you go inverse EE. So a solution has a pH of 5.3. Calculate its hydronium ion concentration. So we're going from pH to hydronium ion concentration. You just use the formula. Hydronium ion concentration is 10 to the power of negative pH. So hydronium ion concentration is 10 to the power of negative 5.3. And we simply let the calculator do its job, 5.0118 times 10 to the negative 6. If we were picky, we have to go to 2 decimal places. Remember, this doesn't count. So it just should be 5.01, right? For the, oh no, the pH only has 1. That's silly. It's only this guy that's significant, right? So that's why it's only 2, 1. So although pH is used more commonly, in some applications it's more practical to describe hydroxide ion concentration, and we call that pOH. The definition of pOH follows the same format as pH. So in order to find the pOH, you use negative log of the hydroxide ion concentration, and in order to find the concentration of the hydroxide ion, you just go 10 to the power of negative pOH. This doesn't change, kiddos. You still have the negative here, and it's still the negative log. So it's all the same. It's just if you're looking for pH or pOH. Here's an example. Calculate the hydroxide ion concentration of water with a pOH of 6.3. No sweat. It's the same formula. So now you're just looking for the concentration of the hydroxide ion, and you just use 10 to the power of negative pOH, and you just take that 6.3, that becomes, that goes there, and make sure you have the negative because it's the negative pOH, and you get your answer as 5 times 10 to the negative 7 moles per liter. So let's summarize. pH is equal to negative log of the hydronium ion. That's to find the pH. To find the hydronium ion concentration, it's 10 to the power of negative pH. pOH, to find the pOH, you just go negative log of the hydroxide ion concentration. And to find the hydroxide ion concentration is just 10 to the power of negative pH. The number of digits following the decimal point in a pH or pOH value is equal to the number of significant digits in the corresponding hydronium or hydroxide ion concentration. And for both pH and pOH, an inverse relationship exists between the ion concentration and the pH or pOH. The greater the hydronium ion concentration, okay, so the greater the hydronium ion concentration, the lower the pH. Kind of cool. Another thing you guys need to know, and I'll just put on the next slide, is this is very important because we talked about it earlier that there's pOH, there's depending on what you're testing for, if you're measuring pH, right, you're measuring the concentration of the hydronium ions, and for pOH, it's actually the measurement of the hydroxide ion concentration. We also talked about that there's hydroxide ions in everything, including acids, just very little amount. In a base, there's higher amounts of hydroxide than there is hydronium ion concentration. So this is really important. pH plus pOH is equal to 14. Always, always, always. This is very important. Okay, it's kind of implied, but I thought I'd write it down for you so you use this. So if I have a pH of a substance that is 8, let's say the pH is 8, and I want to know what is the pOH. If the pH is equal to 8, how do I find the pOH? It's just 14 subtract 8, which is equal to 6. So it's that simple. That's simple. That's very important, kiddos, because it just really simplifies our understanding of the relationship between pH and pOH. You can't have one without the other. Okay, have a good one.